66 million years ago, an object roughly the size of a city slammed into Earth at 64,000 kilometers per hour. Within months, 3/4 of all species on the planet were wiped out. This satellite image shows the geographic footprint of the modern-day Yucatán Peninsula in Mexico. Buried deep beneath this landmass is the epicenter of that devastation, the Chicxulub crater, spanning 180 kilometers across. For decades, geologists studying this site have faced a problem. They have a colossal impact zone, but no physical trace of the impacting object itself. The rock is missing because the sheer kinetic energy generated by the crash caused the entire asteroid to instantaneously vaporize into a superheated gas. Without knowing the precise chemical makeup of that vanished rock, scientists have lacked the data needed to accurately model how this event triggered a global climate collapse. This photograph shows a dark horizontal band of clay separating two distinct geological eras. As the superheated gas from the impact cooled, it settled across the entire globe as a millimeter-thin layer of ash known as the KT boundary. Recently, an international research team from British Columbia, Paris, and Brussels probed this tiny layer to see if it held clues to the rock's identity. They extracted highly precise nickel isotope measurements from the clay. By analyzing the variations in these nickel atoms, the team isolated the distinct alien chemical signature of the impactor from the background noise of Earth's own geology. This isotopic profile acts as a permanent chemical signature. Even though the physical rock was destroyed 66 million years ago, its chemical ghost remains, allowing researchers to finally identify the space rock that struck our planet. The chemical signature identifies the impactor as a CO chondrite. These distinctive rounded inclusions are primitive, untouched relics from the birth of the solar system. To understand how unusual this is, consider the numbers. Carbonaceous chondrites make up only 5% of all meteorites sampled on Earth. Within that small group, the CO chondrite classification is a microscopic fraction. This impactor was a true astronomical oddball. These ancient rocks likely originated far from the Sun, drifting in the debris-laden regions of the outer asteroid belt near the orbit of Jupiter. This 165 million-year dynasty ended through a rare astronomical statistical anomaly, a rogue rock from the absolute edge of the inner solar system. This identification reveals a critical chemical trait of the impactor. CO chondrites contain incredibly low amounts of volatile elements, specifically sulfur. For decades, scientists believed the asteroid itself carried the sulfur that vaporized on impact to create a sun-blocking atmospheric shield. This discovery clarifies the model. The space rock itself lacked the volatile chemistry required to flood the atmosphere with sulfur and freeze the planet. If the deadly sulfur didn't come from space, it was supplied by the Earth itself. The impact's kinetic force pulverized unimaginable quantities of the Yucatan's sulfur-rich limestone bedrock, blasting it directly into the stratosphere. The kinetic energy of the impact turned our own planet's crust into a weapon. It was this pulverized limestone that choked the atmosphere, blocked the sun, and starved the dinosaurs. When you look at the mechanics of this event, the sequence requires a staggering level of bad luck. If this rare rock had struck just a few minutes earlier or later, it would have hit the deep ocean instead of sulfur-rich limestone, potentially leaving the entire dinosaur dynasty intact. The extinction was the ultimate cosmic dice roll. A rare space anomaly arrived at the exact moment to turn Earth's geology against its inhabitants.